Well, let me tell you a story about something that bothered Albert Einstein for the last 30 years of his life. It bothered him so much that he spent decades trying to prove it couldn't be real. He failed. And the reason he failed is one of the strangest, most beautiful things in all of physics. Create two particles in an entangled state. Two photons, say, with correlated polarizations. Separate them. Put one in New York, one in Tokyo. Put one on Earth, one on Mars. Put one here, one on the other side of the galaxy, billions of light years away. Now measure one photon's polarization. The instant you do that, faster than light could possibly travel between them, the other photon's state is determined. Not revealed. Determined. Before you measured, neither photon had a definite polarization. They were in superposition, existing in all possible states at once. But measure one, and both collapse to correlated states simultaneously, instantaneously, across any distance. Einstein called this spooky action at a distance. And you know what? He was right that it's spooky. He was just wrong that it's impossible. This is real. This happens. Every single day in laboratories around the world, physicists create entangled particles and watch them do exactly this. And in 2022, the Nobel Prize in Physics went to three scientists who spent their careers proving that Einstein was wrong about this. Not wrong about relativity, not wrong about the speed of light, wrong about the nature of reality itself. Now you see, Einstein didn't just dislike this idea, he thought it revealed a fatal flaw in quantum mechanics. The theory was incomplete, he said. There must be hidden variables we haven't discovered yet. Properties that particles have all along, even when we're not looking. The universe, Einstein believed, is made of things with definite properties, real things, local things. Things that can't instantly affect each other across vast distances. He was wrong about that. Let me tell you what happened. It's 1935. Einstein is at Princeton. He's frustrated with quantum mechanics, with Niels Bohr, with this whole Copenhagen interpretation business that says particles don't have definite properties until you measure them. So Einstein, along with two colleagues, Boris Podolsky and Nathan Rosen, publishes a thought experiment, a challenge. They called it the EPR Paradox after their initials. Here's what they imagined. Take two particles that have interacted and become entangled. These particles have perfectly correlated properties. If you measure one particle's position, you instantly know the other's position. If you measure one particle's momentum, you instantly know the other's momentum. Now, here's the clever part. You can choose which measurement to make after the particles have separated, after they're far apart. And your choice can't affect the distant particle, right? That would require faster than light influence, which violates relativity. Einstein assumed locality, the principle that distant objects can't instantly influence each other. So, Einstein argued, both properties must have definite values all along, position and momentum. They're just hidden from us. Quantum mechanics is incomplete. There are hidden variables we haven't discovered yet. The argument seemed airtight. For decades, it stood as a serious challenge to quantum mechanics. But Einstein made a mistake. He assumed you could have both reality and locality, that particles have definite properties and that those properties can't be instantly affected by distant measurements. Experiments would show that one of those assumptions has to go. Now, for a long time, this was just philosophy, just arguing. Einstein said one thing, Bohr said another. Nobody knew how to test it. But then, in 1964, something remarkable happened. There was a physicist named John Stuart Bell working at CERN, very brilliant fellow. And Bell proved something extraordinary. He proved that no local hidden variable theory could reproduce all the predictions of quantum mechanics. He derived an inequality, Bell's inequality. It's a mathematical relationship that any local realistic theory must satisfy. Local meaning no faster than light influences. Realistic meaning particles have definite properties before measurement. Bell showed that if you measure correlations between entangled particles in certain ways, local hidden variable theories predict one result. Quantum mechanics predicts a different result, and the predictions disagree. This transformed everything. The EPR argument went from philosophy to experiment. You could actually test it. Build entangled particles, measure correlations, check if they satisfy Bell's inequality. If they do, maybe hidden variables work. If they violate the inequality, either locality fails or realism fails. Either particles don't have definite properties before measurement, or measuring one particle instantly affects the other. Either way, our intuition about reality is wrong. Think about that for a second. You can actually test the nature of reality in a laboratory. And you know what happened? In 1982, a physicist named Alain Aspect, working in France, performed the experiment. He created pairs of entangled photons. He measured their polarizations at different angles. He checked the correlations. And the results violated Bell's inequality. Quantum mechanics was right. Local realism was wrong. But here's the thing. Skeptics raised objections. They called them loopholes. Maybe the detectors were inefficient, only detecting certain photons and missing others. Maybe that biased the results. They called this the detection loophole. Or maybe the measurement settings weren't truly random. Maybe somehow the particles knew in advance which measurements would be performed, the freedom of choice loophole. Or maybe, just maybe, the particles communicated during the measurement. Maybe the detectors weren't far enough apart. The locality loophole. For decades, physicists worked to close these loopholes, one at a time, then all together. In 2015, three different experiments in Delft in the Netherlands, in Vienna in Austria, and in Boulder in the United States performed what they called loophole-free Bell tests. They used fast random number generators, quantum random number generators, to choose measurement settings. The choice was made so late that even light couldn't travel from the measurement device to the particle before the decision was made. They separated the detectors by kilometers. In the Delft experiment, 1.3 kilometers. Light takes over 4 microseconds to travel that distance. The measurements were completed in microseconds, faster than light could travel between detectors. No communication possible. And they achieved high detection efficiency. Over 75% of photons were detected. All three experiments violated Bell's inequality, decisively, unambiguously. In 2022, the Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger for these experiments. The Nobel Committee was explicit. Entanglement is real. Non-locality is real. The universe does not respect our intuitions about separability, about objects being independent when they're far apart. Now, you see, this is where people get confused. They hear non-locality and they think, aha, faster than light communication. We can send messages instantly across the galaxy. No, 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 no. Entanglement doesn't allow communication. Here's why. When you measure an entangled photon, you get a random result. Say you're measuring polarization. 50% chance horizontal, 50% chance vertical. It's truly random. You can't control which result you get. You can't encode a message in your measurement. You can't decide to get horizontal or vertical. Nature decides. And only when you compare your results with the distant measurement do you see the correlation. Your result is random. The distant result is random. But they're correlated in a way that violates classical expectations. The correlation is instantaneous. But accessing it requires classical communication. You have to send your measurement results to the other person at light speed or slower. Only then can you see the correlation. You can't use entanglement to send information faster than light. This preserves causality. No time travel paradoxes, no grandfather paradoxes. Entanglement is correlation without causation, connection without communication. But that doesn't make it less strange, it makes it more strange. Because what it means is that measuring one particle genuinely changes the other particle, instantly, across any distance. Or, alternatively, particles don't have definite properties until measured. Both options violate something we thought was fundamental about reality. Let me tell you about something called quantum teleportation. Now, the name makes it sound like science fiction, but it's real. It's been demonstrated in laboratories around the world. Here's how it works. You have two entangled particles, call them particle A and particle B. Particle A is with Alice. Particle B is with Bob. Bob can be far away, across the room, across the earth, across space. Now Alice has a third particle, particle C, with some quantum state, some particular polarization or spin or whatever. Alice wants to transmit that state to Bob. She doesn't want to send particle C itself. She wants Bob's particle B to end up in the same state that particle C was in. Here's what she does. She performs a special kind of measurement on particles A and C together. This measurement entangles them and destroys the original state of particle C. You can't clone quantum states, there's a theorem about that. But the measurement gives Alice some information. 2 classical bits. She sends those 2 bits to Bob through normal communication channels, light speed or slower. When Bob receives the 2 bits, he performs one of 4 possible operations on his particle B, depending on which bit he received. And now, particle B is in the exact state that particle C was in originally. The quantum state has been teleported from Alice to Bob. The state never traveled through the space in between. Particle C's state was destroyed. Particle B acquired that state, and the whole thing required entanglement plus classical communication. You can't teleport faster than light because you need those 2 classical bits, but you can teleport quantum states across hundreds of kilometers. In 2017, Chinese scientists teleported quantum states from a ground station to a satellite orbiting Earth, over 1,400 kilometers away. In 2024, experiments achieved quantum teleportation over terrestrial fiber optic networks spanning thousands of kilometers. This is the basis for proposed quantum networks. Quantum Internet. Completely secure communication using the laws of physics themselves. This is not speculation, this is engineering. Now, let me tell you what entanglement really means, what it says about the nature of reality. You see, when 2 particles interact and become entangled, they stop being 2 separate things. They become one system, one joint wave function. You can't describe one particle without describing the other. They're connected. Not by signals, not by hidden wires, but by the wave function itself. And this connection doesn't diminish with distance. Separate the particles by a meter, by a kilometer, by a light year, by a billion light years. The connection remains. Measure 1, and the joint wave function collapses. Both particle states are determined simultaneously. In a sense, the universe is one vast entangled state, everything connected to everything through past interactions. You're made of particles that have interacted with other particles. Those particles came from stars, from the Big Bang, from interactions spanning cosmic history. Every atom in your body has interacted with countless other atoms. Entanglement spreads. Decoherence happens, yes, which is why you don't see macroscopic entanglement in everyday life. But at the fundamental level, the universe isn't made of separate independent objects. It's one interconnected whole. Locality, the idea that distant objects can't influence each other, is wrong. Or realism, the idea that objects have definite properties independent of observation, is wrong. Or both are wrong. There is no interpretation of quantum mechanics that preserves both and matches experiment. You have to choose. You have to abandon something you thought was fundamental. Most physicists, I think, abandon realism. They accept that particles don't have definite properties before measurement. The Copenhagen interpretation, more or less. Wave functions are real and they collapse upon measurement. But some physicists try to preserve realism by abandoning locality. Pilot wave theory, Bohmian mechanics. In these interpretations, particles do have definite positions all along, but there's a quantum potential that connects them non-locally. Faster than light influences are real, but they're arranged such that you can't use them to send information, so causality is preserved. And then there are interpretations like many worlds, where both particles and measurements have definite outcomes, but the wave function never collapses. Instead, the universe splits into multiple branches. Every possible outcome happens in some branch. Entanglement is correlation between branches. This preserves determinism and realism, but at the cost of accepting an infinity of parallel universes. Nobody knows which interpretation is correct. Nobody even knows if the question is meaningful. The experiments agree with the math. The math is quantum mechanics. But what the math means, what reality is actually like beneath the equations, we don't know. Maybe we can't know. Maybe the universe doesn't have to make sense in human terms. Richard Feynman, who understood quantum mechanics as well as anyone, said this. He said, "I think I can safely say that nobody understands quantum mechanics." And he also said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." This is a theory that works perfectly. It predicts experimental results to 15 decimal places. It's the most precisely tested theory in all of science. And yet, we don't know what it means. We don't know what's actually happening. Entanglement is the clearest example of this strangeness. It's the phenomenon that forces us to choose which cherished assumption to abandon: locality or realism, separability or definiteness. We can't have both. The universe won't let us. In 2022, when the Nobel Committee awarded the Physics Prize to Aspect, Clauser, and Zeilinger, they wrote this. They said these scientists had demonstrated the violation of Bell inequalities and pioneered quantum information science. They had shown that quantum mechanics cannot be explained by local hidden variables. They had proven that Einstein was wrong about the completeness of quantum mechanics. Think about what that means. Einstein, Albert Einstein, the man who gave us relativity, the man who explained the photoelectric effect, Brownian motion, the equivalence of mass and energy, the man who understood space-time curvature, gravitational waves, the cosmological constant. That Einstein spent 30 years trying to prove quantum mechanics was incomplete. And he was wrong. Not wrong about relativity. Not wrong about the constancy of the speed of light. Wrong about whether the universe could be spooky. Wrong about whether particles could be connected across space. Wrong about whether reality could be this strange. And you know what? I think that's beautiful. Even the greatest minds in history can be surprised by nature. Even Einstein's intuition failed when confronted with quantum mechanics. The universe is under no obligation to match our expectations. It's under no obligation to make sense. It simply is what it is. And what it is, apparently, is weirder than we ever imagined. Entanglement says that when you look at two particles that have interacted, you're not looking at two things. You're looking at one thing that happens to be in two places, or you're looking at two things that don't have definite properties until you look. Either way, the world isn't what it seems. Objects aren't separate, space doesn't isolate, distance doesn't protect. Measure a photon's polarization here, and its entangled partner knows instantly across the galaxy. Not because a signal traveled between them, not because they agreed in advance, but because they were never truly separate to begin with. They're part of one quantum state, one wave function, one reality. And we are part of that reality. Every particle in your body has been entangled with other particles at some point in cosmic history. You're made of stuff that came from stars, from supernovae, from the Big Bang itself. Stuff that has interacted and entangled and spread across the universe. You are not separate from the cosmos. You are the cosmos, examining itself through the improbable mechanism of human consciousness. Einstein found this idea intolerable. He believed in a universe of things, real things, with definite properties, existing independently whether we look or not. A universe where space separates, where locality protects, where distant events can't instantly affect each other. He believed, as he once wrote, that the moon is there even when nobody looks. Maybe he was right about the moon, but he was wrong about photons, wrong about electrons, wrong about the fundamental constituents of reality. They are not there with definite properties when nobody looks, or if they are, they connected non-locally, instantly across space. The experiments have spoken. Bell's inequality is violated. Local realism fails. Einstein's intuition, powerful as it was insufficient to grasp the true strangeness of quantum mechanics. And here we are, made of atoms and energy and quantum fields, trying to understand how it all works. Trying to grasp the nature of reality with brains evolved to hunt and gather on the African savannah, and somehow, improbably, we've succeeded. Not completely, We don't understand what quantum mechanics means. But we understand what it predicts. We can manipulate entanglement. We can perform quantum teleportation. We can build quantum computers that exploit superposition and entanglement to solve problems classical computers never could. In a way, we've learned to speak the universe's language, even if we don't fully understand what we're saying. Entanglement is real. Non-locality is real. The universe is not made of separate objects. This is not speculation. This is not interpretation. This is experimental fact confirmed by decades of research, recognized by a Nobel Prize, and used in technologies being developed right now. Einstein called it spooky. He was right. It is spooky. It violates our deepest intuitions about how reality should work. But it is how reality does work. And that, I think, is more wonderful than any intuition we could have imagined. The universe is stranger than we thought, stranger than we can think, maybe. But we can still study it. We can still understand the mathematics, perform the experiments, see the correlations. We can still do science. And that is how physics is. You discover something beautiful, something that works, something that predicts nature with extraordinary precision. And then you find something you cannot explain, something that seems impossible, something spooky. And you have to choose. Do you reject the mathematics because they violate intuition? Or do you accept that intuition is wrong and follow the mathematics wherever they lead? Einstein chose intuition. The universe chose mathematics. And we're left with a reality where particles are connected across space, where measurement has consequences that travel faster than light, without allowing communication, where objects don't have definite properties until observed, or where they do but are guided by non-local influences, or where every possibility happens in some branch of an infinite multiverse. We don't know which picture is correct. Maybe none of them are. Maybe reality is something we can't picture at all. But we know what the experiments show. We know that Bell's inequality is violated. We know that entanglement is real. We know that Einstein, for all his genius, was wrong about this. And somehow, that makes the universe more wonderful, not less.